Hi everyone, this is Sridhar Chintala, Assistant Professor of Physics, ABV Government Degree College, Janagaon. So far I'm making video lectures on statistical mechanics. This is the second video lecture on statistical mechanics, and the statistical mechanics is from the second semester of BSc Physics according to the Kakti University syllabus. So in this statistical mechanics, I'm going to discuss about the statistics, different statistics. So as a part of the statistics, we are discussing about the Maxwell-Boltzmann statistics. So Maxwell-Boltzmann statistics. So this is in BSc Physics, Thermal Physics, second semester, and this is in the unit 4 named as the statistical mechanics. So as far as statistical mechanics is concerned, the postulates of statistical mechanics are if all gases are composed of molecules which are in a state of constant random motion, the total number of molecules in a gas is constant, the total energy of the system is constant, all the elementary cells are of the same size, all the accessible microstates corresponding to possible microstates are equally probable, and the equilibrium state of a system corresponds to state of maximum probability. So this has already been discussed in the introduction to the statistical mechanics. That is the reason why I'm going a little fast. So then the statistics is divided majorly into two parts or two statistics. One is classical statistics and the second one is the quantum statistics. So as far as the classical statistics is concerned, it uses the Maxwell-Boltzmann distribution law and the Maxwell-Boltzmann velocity distribution of particles for an assembly of an assembly in equilibrium. So this is the classical statistics, and whereas the quantum statistics is majorly divided into two types. One is the Bose-Einstein statistics, and the second one is the Fermi-Dirac statistics. So in order to explain the photoelectric effect and quantum effect, the Planck's theory of radiation, the quantum mechanics comes into the picture. So based on the quantum picture or the quantum mechanics, the statistics again developed, that is the Bose-Einstein statistics. So as far as the Pauli's exclusion principle is concerned, when the particles are with half integral spins, so according to Pauli's exclusion principle, another statistics came into existence, that is the Fermi-Dirac statistics. So as far as the statistics is concerned, we are having three types of statistics. One is classical statistics, that is Maxwell-Boltzmann statistics, and the second one is the Bose-Einstein statistics. And the third one is the Fermi-Dirac statistics. So Maxwell-Boltzmann statistics is applied to all the classical particles, and Bose-Einstein statistics as well as the Fermi-Dirac statistics are applied to the quantum particles, and whereas the Bose-Einstein statistics obeys the particles which are having the integral spins or zero spins, whereas the Fermi-Dirac statistics is concerned, the particles obey Pauli's exclusion principle and are having half integral spins, and they are called the fermions. So electrons, photons, neutrinos, neutrons, helium-3 atom are the particles of this kind, and whereas the Bose-Einstein statistics for the bosons, the photons, 5 mesons, and helium-4 atom are the particles of Bose-Einstein statistics are bosons. And then we are moving on to the Maxwell-Boltzmann distribution law. So before going to discuss about the Maxwell-Boltzmann law, just we discuss what is called the, sorry. So what is the difference between the classical statistics and quantum statistics? So as far as the classical statistics is concerned, we may have any number of particles in any cells. So that means there is no restriction on the particles to accommodate in a given cell. Whereas the quantum mechanics is concerned, the size of the cell is restricted by the Heisenberg's uncertainty principle, and the volume of each cell is not less than h cube, so that the number of particles available and the number of energy levels available and the number of particles are equal in the case of quantum mechanics, so that the occupation index in the case of quantum mechanics is almost equals to 1, whereas the occupation index in the case of the classical mechanics is less than 1. So as far as the classical mechanics is concerned, the particles are identical but distinguishable, whereas the quantum mechanics is concerned, quantum statistics is concerned, particles are identical but indistinguishable. So then if you consider the Maxwell-Boltzmann distribution law to explain or to derive the expression for MB distribution law, just we are considering a system of n similar distinguishable particles, and each particle is described by a set of position and momentum coordinates, and therefore an energy is associated with it. An energy eigenvalue of the system is a sum of single particle energies called levels. As the values of position and momentum can take any of the values, these levels forms a continuum. And let us divide the spectrum into groups G1, G2, G3 and so on and so forth levels as shown in figure. So each group is called a cell, has an average energy E1, and let N1, N2, N3 and so on and so forth Nk be the occupation numbers of these cells Z1, Z2, Z3 and so on and so forth Zk. So this is the division of the spectrum into cells or levels. So each level is indicated by a group is G1, G2, G3 and so on and so forth up to Gk, and each group is called a cell, and it is having an average energy E1 if it is a level G1, E2 if it is a level G2, E3 and so on and so forth. For the Gk level, it is energy is Ek. And let N1, N2, N3 and so on and so forth Nk are the occupation numbers of each cells G1, G2, G3 and G4 up to Gk and so on and so forth. So then the conditions. So we have divided the spectrum into groups, and each group is called a cell, and each cell is having some occupation number n. So then the conditions in Maxwell-Boltzmann distribution law are: one is the particles are similar and distinguishable. That is, there are no symmetry restrictions on particles. Each eigenstate of the ith group contains 0, 1, 2, 3 up to so on and so forth Ni particles, and therefore an energy is associated with it. So the total number of particles in the entire system is always constant. So as far as the Maxwell-Boltzmann distribution law is concerned, the particles are similar and distinguishable. So as they are distinguishable, so there is no symmetry restriction on the particles. Each eigenvalue of the ith group contains, so for if you consider any ith state, it may contain 0 particles or 1 particles, 2, 3, so on and so forth up to Ni. So the number of the state particles, and therefore an energy is associated with it. And as far as the system is concerned, the total number of particles in the entire system is always constant. That is, if you consider capital N is equal to N1 plus N2 plus N3 and so on and so forth up to Nk, that is N1 is the number of particles in the first level, and N2 is the number of particles in the second level, and so on and so forth. If you consider the total number of particles is equals to constant. That is summation I from 1 to n, Ni is equals to a constant. Then if you take the change in the number of particles, that is given by delta n is equals to delta n1 plus delta n2 plus delta n3 and so on and so forth up to delta nk is equals to 0. That is summation I runs from 1 to k delta ni is equals to 0. So this is the total number of particles of the entire system is constant. And the fourth one is the total energy of the system is constant. That is the sum of energies of all the particles in different groups taken together constitute the total energy of the system, and which is a constant. And hence we have capital E, the total energy E is equals to N1 number of particles are having energy E1, and N2 number of particles are having energy E2, and N3 particles are having energy E3, and so on and so forth. So this is the total energy of the N1 particles, and this is the total energy of N2 particles, N3 particles, and so on and so forth. And if we take the sum of all the energy, this will give the energy of the system, and that is equals to a constant. And if you want to observe the change in the energy, that is delta E is equals to E1 into delta N1 plus E2 into delta N2 plus E3 into delta N3. So whereas we are taking the only variation in the number of particles, as the energy of the system is constant, that is the level is constant. So we may have any number of particles in that level, but the energy of that level is fixed. So as the energy of the level is fixed, we are not taking the variation in energy. So we are taking the variation in number of particles only. So delta E is equals to E1 delta N1 plus E2 delta N2 and so on and so forth. Ek delta Nk is equals to 0. That means the total number of, the total energy of the system is constant. And if you want to take the variation, that variation must be equal to 0. This is the fourth condition and fourth assumption, we may call it as. And then in the distribution, if you consider in the Maxwell-Boltzmann distribution, the gas molecules are distinguishable and are divided into groups N1, N2, N3, and so on and so forth. Already we discussed. Each spectrum is divided into groups. Each group is G1, G2, G3, and so on and so forth. And in each group, there may be number of particles or number of molecules. And those number of molecules are N1, N2, N3, and so on and so forth. So in this distribution, if there are N1 molecules in the first state and N2 molecules in the second state and Ni molecules in the ith state or Nk molecules in the kth state. So if in any state you consider, there are some molecules and that molecules are indicated as N and 1, the subscript indicates the level. So there can be any number of ways, there can be a number of ways in which this configuration can be achieved. So N1 in 1 or N2 in 2, N3 in 3. So this configuration can be achieved in different ways or in number of ways. So the thermodynamic probability is the distribution of different sequences in which the balls may be distributed among the cells without changing the number in each cell. So here we are considering the level 1, it is having N1 molecules. And these N1 molecules may arrange in the given level in N1 factorial ways. And if you take the N2, so it will take N2 factorial ways. So that means each level is arranged in different sequences. So the thermodynamic probability is the distribution of different sequences in which the balls may be distributed among the cells without changing the number in each cell. And hence, the number of ways in which N1 molecules out of total N molecules may fall in the first state. So the first state will consisting of N1 molecules, and we may select N1 molecules from the capital N molecules, and that is given by NCN1 is equals to N factorial by N1 factorial into N minus N1 factorial. So this is the number of ways we can choose the N1 molecules in the first level out of capital N molecules. And then after choosing the N1 molecules, So the second level, the number of ways in which N2 molecules out of remaining N minus N1 molecules can be placed in the second state are N minus N1 C N2 is equals to N minus N1 factorial by N2 factorial into N minus N1 minus N2. And if you consider the third level, that will be N minus N1 minus N2 C N3 is equals to like that. So the number of ways in which N3 molecules can be placed out of remaining N minus N1 minus N2 molecules in the third state are, so this is the case, capital N minus N1 minus N2 C N3 is equals to capital N minus N1 minus N2 factorial by N2 factorial, so this is N3 factorial into N minus N1 minus N2 minus N3 factorial. It should be N3 here, and so on up to Nk molecules for kth state. So the total number of ways in which the molecules in different states may be exchanged, leaving the total number in each state is fixed, is given by sum of all the probabilities or sum of all the distributions. So n factorial by n1 factorial into n minus n1 factorial into n minus n1 factorial by n2 factorial into capital N minus small n1 minus small n2 factorial into capital N minus n1 minus n2 factorial by n2 factorial. So this is n3 factorial into n minus n1 minus n2 minus n3 factorial, and so on and so forth. And for the kth level, n minus n1 minus n2 and so on and so forth up to nk minus 1 factorial by nk factorial into n minus n1 minus n2 minus n3 and so on and so forth up to nk factorial. And if you observe this product, here we are having n minus n1 factorial in the denominator and n minus n1 factorial in the numerator, and these two will be cancelled. And here n minus n1 minus n2 minus n2 factorial in the denominator, and in the numerator also we are having the same term. So likewise, all the terms will be cancelled, and we are left with the n factorial and n1 factorial, n2 factorial, n3 factorial, and so on and so forth. So if you take the product, the total number of ways in which the molecules of different states may be exchanged, leaving the total number in each state is fixed, is given by n factorial by n1 factorial into n2 factorial into n3 factorial, and so on and so forth, nk factorial. So this may be gives the relation or the expression for the thermodynamic probability of the distribution, and that may be expressed. And now let each group Gi be described by Gi elementary wave functions. So we have G1, G2, G3, G4 and up to Gk levels. And if you consider any intermediate level, that is intermediate group Gi, that can be described by the Gi elementary wave functions and therefore Gi energy levels. If you consider the ith group, the particles are accommodated in Gi different levels. The first molecule of Ni can be accommodated in any of the Gi levels in which can be done in Gi ways. So we are having a group Gi. In that group, we are having some levels, Gi energy levels. So if one particle sits in any of the level, and that can be in Gi levels. For example, one ball is to be placed in 12 boxes. So how many ways we can put it? We can put it in 1, we can put it in 2, we can put it in 3 or 4, 5, 6 and 7 up to 12. So there are 12 ways in which we can put a ball in the box. So in that way, so if you consider the ith level, which is consisting of Gi energy levels, so if you want to put the first molecules of Ni in, it can be accommodated in any of the Gi levels in Gi different ways. And the second molecules can also be accommodated in GI ways, and third molecule, and also, since there is no restriction on this molecule. So likewise, if we consider, if all the N1 molecule, Ni molecules can be occupied in GI levels, if all the molecules are occupied, then Ni molecules are occupied in GI levels, and the ways is given by GI to the power of Ni. So therefore, the a priori probability that Ni molecules occupying simultaneously the ith level is Gi to the power of Ni. So this is the probability in which the Ni molecules can occupy the Gi levels in the ith level. And if you consider the a priori probability of any particular distribution of n balls among the k states, such that the N1 molecules occupying the first state of the molecules, and N1 molecules occupying the first state and N2 molecules occupying the second states, and N3 and so on and so forth, if you want to write. So that is given by Gi to the power of N1, Gi to the power of N2, Gi to the power of N3. These are all multiplied with one another. So the product is given by the a priori probability of any particular distribution of n balls among the k states, such that the N1 molecules are occupying the first state and the N2 molecules are occupying the second state, and that is given by this one. And the number of distinguishable ways in which n molecules can be distributed among the possible energy levels is given by, so this is the occupying and this is the probability. So the total distinguishable ways in which n molecules can be distributed among possible energy levels is given by P is equals to N1 capital N factorial by N1 factorial into N2 factorial and up to Nk factorial, and this multiplied with the distribution occupation index. So this is given by N factorial into pi I from 1 to N, and then this is Gi to the power of Ni by Ni factorial. So the probability of the given state is given by P is equals to capital N factorial into pi I is equals to 1 from 1 to N, and Gi to the power of Ni by Ni factorial. And the natural logarithm of equation 6.6 gives the log P is equals to log N factorial minus summation Ln, that is the log Ni factorial, plus summation Ni log Gi. And this is the Stirling approximation, and the Stirling approximation is given by log N factorial is equals to N log N minus N. So this is the Stirling approximation. We are taking the final result of the Stirling theorem. So we are applying this to the above expression, and we get ln P is equals to capital N into ln capital N minus summation Ni ln Ni plus summation Ni plus Ni log Gi. So here this is capital N and this is summation Ni, and this is nothing but capital N. So these two terms will be cancelled each other, and this is log P is equals to capital N log N minus summation Ni log Ni plus summation Ni log Gi. So this is the probability of distributing n number of molecules in any of the energy levels, available energy levels. So for the most probable distribution, P is maximum subjected to the restriction that the total number of particles n and total energy are constants. So for the most probable distribution, the P is maximum when it is maximum is the total number of particles and the total energy is constant. So from equation 7, we have for maximum P as log P maximum is equals to the variation in the molecules. So if you consider this as n is equals to constant, the total number of molecules is equals to constant. So the variation in this will be equal to 0. And this is minus summation ni, as this is log ni, this is 1 by ni delta ni minus. So if we differentiate as uv, this is 1 and this is another one. So minus summation log ni into delta ni plus summation ni is a variable and gi is not the variable, so it is we are writing L log gi into this is the delta ni is equals to 0. For the maximum probability, the variation in this will be equal to 0. Since delta ni is equals to 0, this one is going to be equal to 0. Sorry, here ni will be cancelled. So in this term ni will be cancelled and we are left with ni. So summation ni is equals to 0. So we are left with the summation log ni into delta ni plus ln the log gi into delta ni is equals to 0. This is equation 8. And we are considering the conditions. The conditions are the total number of molecules and the total number of energy. The total energy of the system is constant. So from that conditions, if you multiply those conditions by some constants and adding to the equation 6.8, we are having so we have summation delta ni is equals to 0 and we have summation ei delta ni is equals to 0. Yeah. So we are multiplying this by some constant alpha and we are multiplying this by some constant beta with the negative signs. So and adding these two to the equation, the earlier equation 6.8. So we have this one. So these are the two terms which are already there in the equation 6.8 and we are adding these two terms extra with the delta alpha ln I, sorry, sigma alpha delta ni. So that is the summation alpha into delta ni minus summation beta into epsilon, sorry, ei into delta ni. So this is equals to 0. So this is the equation we got finally, and as delta ni's are independent variables, for the validity of the last equation, the quantity within the brackets must be always be 0 for each value of I. Summation delta ni is equals to 0, but delta ni is not equal to 0. As delta ni is not equal to 0, this term must goes to be 0. So that is the reason we are having minus log ni plus log gi minus alpha minus beta ei is equals to 0. Right. So if you remove the logarithm, we will get exponential. So it is ni is equals to. So we are bringing this ni to this side and this becomes positive. So ni is equals to gi into e power minus alpha into e power minus beta ei. And if you rearrange this equation, you will get ni is equals to gi by exponential of alpha plus beta ei. So this is called the Maxwell-Boltzmann distribution law. So the equation is called the Maxwell-Boltzmann distribution law, and one can show that e power minus alpha is equals to nh cube by v into 1 by 2 pi m kt to the power of 3 by 2 and beta is equals to 1 by kt. And if you substitute beta is equals to 1 by kt in the above equation, we will get beta Ni is equals to Gi by exponential of alpha plus Ei by Kt. And the number of molecules per cell decreases exponentially with energy E associated with the cell. This means that low energy cell contains more molecules than the higher energy cell. So this is about the Maxwell-Boltzmann distribution law. And we can apply this Maxwell-Boltzmann distribution law in order to find the energy levels of an ideal gas. So molecular energies in an ideal gas. So let us consider an ideal gas of n molecules contained in a volume V at an absolute temperature T. The number of molecules with energy between E and E plus dE can be obtained from Maxwell-Boltzmann distribution law. According to Maxwell-Boltzmann distribution law, the most probable distribution of molecules among various energy levels is given by Ni is equals to Gi into e power minus alpha into e power minus beta Ei, and it is convenient to consider continuous distribution of molecule energies rather than discrete energies, that is E1, E2, E3 and so on and so forth. So when you consider the continuous distribution of energies, the equation 6.12 becomes N of E is into D of E is equals to G of E into e power minus alpha into e power minus E by Kt dE. So NEDE represents the number of molecules having energies between E and E plus dE, and where GE into dE represents the number of states that have energies between E and E plus dE. So this NEDE represents the number of molecules and GEDE represents the number of states. So let us first evaluate what is G of E into dE. And a molecule of energy E has a momentum P whose magnitude is given by P is equals to under root 2 ME. That is the summation of Px square plus Py square plus Pz square under root. So where Px, Py, Pz and Px, Py and Pz are the components of momentum along x, y and z directions respectively. So each set of momentum components specifies a different state of motion. Let us consider or let us imagine a momentum space whose coordinate axes are Px, Py, Pz, and the number of momentum states available to a molecule within a momentum whose magnitude is in between P and P plus dP is proportional to the volume of the spherical shell in momentum space of radius P and thickness dP, and volume of the spherical shell is 4 pi P square dP, and hence Gp dP is equals to Bp square dP. So when you consider the momentum components of Px, Py, Pz, the number of momentum states available to a molecule within a momentum whose magnitude in between P and P plus dP is proportional to the volume of the spherical shell in momentum space of radius P and thickness dP. So this is the number of momentum states available for a molecule whose momentum fall in between P and P plus dP. Since each momentum magnitude P corresponding to single energy E, the number of energy states dE, G of E into dE between E and E plus dE is the same as the number of momentum states Gp dP between P and P plus dP. So as P is directly proportional to root E, so we can take the probability of energies as probability of momentums. So the number of momentum states is equals to the number of energy states. So GE dE is equals to Bp square dP, and P square is equals to 2 ME, and dP is equals to MdE by root 2 ME, and substituting this into the above equation, G of E dE is equals to B into 2 ME to the power of half into MdE, and this is given by under root 2 m to the power of 3 by 2 into b into under root e into d. And substituting this value in the equation, n of e into de is equal to g of e into d into e power alpha into e power minus alpha by e by kt into de. So we have N of E into dE is equals to root 2 into m to the power of 3 by 2, this one, and B into e power minus alpha, and under root E into e power minus E by kt into dE. So N of E is equals to, we are taking one more constant as C into under root E into e power minus E by kt dE, where C is another constant is equal to root 2 into m to the power of 3 by 2 into B into e power minus alpha, which is a constant. And we can find this constant by the normalization condition. Therefore, from the normalization condition, n is equals to, from integral 0 to infinity n of E into dE is equals to N of E into dE is this. So C into integral 0 to infinity in under root E into e power minus E by kt into dE. And this is in the form of root x into e power minus x formula. So the value of this is given by 1 by 2a into under root pi by a. So this will be equal to n is equal to C. This is C into 1 by 2a. A is the 1 by kt into under root pi by 1 by kt, and this gives a value of n is equals to C into under root pi by 2 into kt to the power of 3 by 2. So this is the value of capital N, that is number of molecules, and from this we can write the value of C, and C is given by 2 pi n by pi kt to the power of 3 by 2. So hence we have N of E of dE is equals to 2 pi n into 1 by pi kt to the power of 3 by 2 into e power half into e power minus E by kt into dE. So this is the Maxwell-Boltzmann distribution law. This is the molecular energy levels of an ideal gas using the Maxwell-Boltzmann distribution law. And when the energy is the available energy levels is plotted against the energy, we got a distribution like this. So as the energy is increasing, the available energy levels increases and reaches a maximum and again falls to 0. So the total energy of the system is given by capital E is equals to integral 0 to infinity E into N of E into dE. So where N of E into D are the energy levels and E is the energy of each level. So this is the total energy is given by 2 pi n into under root 1 by pi kt to the power of 3 by 2 integral 0 to infinity e power 3 by 2 into e power minus E by kt dE. And this is a definite integral, and value of this definite integral is given by the standard formula. This is equals to 3 by 4 kt to the power of 2 and under root pi kt, and therefore we can have capital E is equals to 2 pi n into 1 pi kt to the power of 3 by 2 into 3 by 4 into kt whole square into pi kt under root. So simplifying this equation, we'll get 3 by 2 into n kt. And if you consider the average energy of an ideal gas molecule, it will be equal to E by N is equals to 3 by 2 kT. This is nothing but the law of equipartition of energy, which uses the kinetic theory of gases, what is called the Maxwell velocity distribution law. So this is about the Maxwell-Boltzmann statistics and the application of Maxwell-Boltzmann statistics for the calculation of molecular energies of an ideal gas. So I think you may have a clear picture about the Maxwell-Boltzmann statistics by listening or watching this video. Thank you for your patient listening. Thank you for your attention. Thank you very much.